The next proof method that we're going to look at is something called proof by cases. So first, we're going to look at an example theorem about real numbers and think about how we would prove it. That is going to lead to us exploring the method of proof by cases. Alright, so suppose you have two real numbers, x and y, and you know that x times y is equal to 0. The question is, what can you conclude from that? Well, what can we say about x and our y? At least one of them is 0. One or both of them is 0. So that's our theorem, or at least our conjecture, which it's going to end up being a theorem once we prove it. Suppose x and y are real numbers and that xy equals 0, then x equals 0 or y equals 0. So let's think about how we're going to prove that. So first of all, we're going to assume what's assumed in the theorem. We're going to assume x and y are real numbers, and we're going to assume that x times y equals 0. Then we're going to show that x equals 0 or y equals 0. So one reasonable thing we can do is take that xy equals 0 and just solve for y. So we have xy equals 0. We multiply both sides by 1 over x. We get y equals 0. We wanted to show that either x equals 0 or y equals 0. We just proved that y equals 0. We should be done, right? Well, not quite. The problem is when we multiply by 1 over x, we were assuming in addition that x was not equal to 0, right? It was a hidden assumption, and if we did it without, making a big deal about it, maybe we could sneak it by our reader, but I guarantee you that Peeves is going to find that error. So what we have to do then is we have to prove this in two stages. We have to take the case x equals 0 and x not equal to 0. Now, we know x is a real number, so x is going to be one of these cases. Either x is going to be 0 or not, right? And so what we're going to do is just prove it for each of those individual cases. So here's the deal, right? Those are the only two possibilities for x. If we can prove both cases, then we've shown the theorem is true for all values of x. So we're going to assume that x and y are real numbers and y equals 0, and we're going to show that x equals 0 or y equals 0. But again, we're going to split that assumption into two possibilities. Case 1 is where x equals 0. Well, it sounds a little bit weird, but we want to show that x equals 0 or y equals 0. Since we're assuming x equals 0, we already have that x equals 0, and so that tells us that one of them is true, and so then the or statement is true as well. So, all done. Case 2 is a little bit more complicated. We take the case x not equal to 0. This is where we're going to multiply xy equals 0 on both sides by 1 over x. When we do that, I've already shown you the work, we're going to end up with y equals 0. We wanted to show that x equals 0 or y equals 0. We showed that y equals 0. We're done. So we show that the conclusion is true for all possible values of x and y. So the proof is complete. So this is in general going to be what the proof by cases process is. We just did proof by cases in that particular theorem. Let me explain it, how it works in general. So in general, we have a theorem that says we assume some assumptions and we show some kind of conclusion. What we're going to do in a proof by cases is break down those assumptions into cases. Each case, the cases put all together should cover all the possible ways that the assumptions can be true, right? So for instance, in that last theorem, the two cases for x are either it's 0 or it's not 0, and that's all the possible ways that a real number can be. Now, for each individual case, you assume the regular assumptions that you have in the normal theorem, but then you also assume whatever assumptions go with that case. So for that case, you assume something extra that goes along with the assumptions in the theorem. And then you have to prove your conclusion for every single case. So if we had 2 cases before, but if you had 4 cases, you'd have to prove the conclusions for each of those 4 cases. And that means you're going to have a separate proof for each case. So there are some advantages to this and some disadvantages. The big advantage is that you get to assume more, right? You get to assume the assumptions of your theorem plus whatever assumptions come with your cases. And that is going to make the proofs easier. And of course, the disadvantage is that you have to do more than one proof. You have to do one proof for each assumption that you make. All right, so let's talk. I'm going to show you how to write this proof. Again, this is more stylistically and being nice to your reader, but I'm going to show you how we take the reasoning that we had in the proof outline that we had a couple slides ago and how we actually use it to solve this theorem. Now, of course, the first thing we're going to do is warn our reader what kind of proof method that we're going to use. But even before that, we got to tell our reader what we're assuming and what we're going to show. So at very beginning, we assume x and y are real numbers. We assume that x, y equals 0, and we show that either x equals 0 or y equals 0. And then we give our reader a warning that, hey, we're going to use a proof by cases, which means we're going to take our assumptions and we're going to split them into cases. And the two cases we're going to choose are, we know that x is a real number, so we must have x equals 0 or x not equal to 0. And we're going to prove each of those cases separately. In the case x equals 0, it follows automatically that x equals 0 or y equals 0, since the first one is true, x equals 0, which proves this case. In the case x not equal to 0, we know that x has a multiplicative inverse, 1 over x. We're going to multiply both sides of the equation xy equals 0 by 1 over x to get 1 over x times xy equals 1 over x times 0, which implies that y equals 0 when we solve that, when we simplify it. Since y equals 0, it follows that x equals 0 or y equals 0, which is what we were trying to prove, and that proves the second case as well. Since we have proved the theorem for all possible cases, this completes the proof. Notice at the end that we've given our reader a heads up that, hey, we proved it. Remember, this is what we wanted to prove. We wanted to prove the theorem in both cases. We just finished it, and that's why we're finishing the proof. All right, so here are some strategies for when you'd use proof by cases. For one, you have a theorem where the assumptions that you have don't feel like enough to prove the conclusion for you. You maybe need another assumption to prove the theorem. The only important part is, once you add that assumption, you got to take care of all the other possibilities as well. The assumptions that you have leave you with too many choices to think about them all at once. You can focus your attention on small parts of the assumption, making each choice a case. And again, make sure you consider all possible choices. Don't just consider one choice and think you're done. One choice just means that, okay, now what about your other choices? You gotta consider those as well. And more specifically, if you have a theorem that says if something or something else, then Q. If P1 or P2, then Q. In other words, if the if part comes as an or statement, each of those cases, P1 and P2, can be your cases. So you assume P1 is true and prove Q, then you assume P2 is true and you prove Q, and that proves the theorem. And as far as writing goes, what sort of things can help you be nice to your reader in this case? Well, of course, just like anything else, you want to state your assumptions and your conclusions without the cases, right? Just as you would in any other proof. Then you let your reader know that you're going to use proof by cases, so your reader's ready for you when you split your assumptions into cases. You let your reader know what the cases are, and sometimes this is necessary, sometimes not. You might have to convince your reader that your cases that you're considering cover all possibilities, right? If it's obvious, then you don't have to say anything, right? When I said either x could be 0 or x could not be 0, there's not going to be anyone swooping in saying, okay, well, there's a third possibility. There's x equals 0, x equals not equal 0, and there might be something else. No, I mean, that was pretty obvious. But there might be a situation where it's complicated enough or it's confusing enough that you might need to provide a clear justification if it is not obvious. When you start proving a case, make sure that you're clear which case you're proving. Make sure you're clear what you are assuming in that particular case, so that when you start using those assumptions, nobody gets confused. And then let your reader know when you've gotten to the last case and have completed the proof. Just like with anything else, you're saying the proof is complete, and so the reader can say, oh, yeah, that's right, that was the last case. We're all done with the proof. As usual, I encourage your own way to do these things. You don't have to state them the way I state them. I very much encourage you to find your own way to explain these things and to make these things clear to your reader. Please don't feel like you have to do them exactly the way I do them. All right, so now the activities that come with this video are called Proof by Cases, and that's on the PDF file that comes with this video.